session. Dr. Yining from Nanjing University.
Ladies and gentlemen, it's my pleasure to report our results on the hydrogenation of carbon dioxide on petrified amorphous nickel alloy particles. It's well known that amorphous alloy has short-range ordering and long-range disordering structure. In 1980, these analytical works reported most results on the use of amorphous alloys as catalysts. Since then, this kind of materials has received much attention because of their high activity and better selectivity than crystalline alloys. In the past 10 years, many researchers have made great efforts in studying catalysis of amorphous alloys. It has been found that amorphous alloys have three unique properties. The first is the amorphous alloys can be produced with wide composition range, not available in crystalline form, which permits the continuous control of electronic properties of active sites. The second is the atoms distribute homogeneously in amorphous matrix. So the surface segregation of the alloy can be avoided. This makes a high concentration of active sites, and moreover, the active sites are dispersed in a uniform environment. The third is the structure of amorphous alloys is non-porous. So the diffusion limitation does not affect the surface reaction. Obviously, all these features are interesting in terms of catalysis. Some authors have studied these amorphous alloys as catalysts for CO hydrogenation. The experimental results indicate that almost all these amorphous structures have higher CO conversion and higher carbon-2 selectivity than their crystalline alloys. And in addition, for some of the amorphous catalysts, the reaction product distribution does not obey the Schurz-Brown distribution. These non-catalytic properties is interesting in fields of carbon wire chemistry. Most of amorphous alloys used in previous study were prepared by quenching method. The amorphous alloys prepared by this method are in the form of ribbons or films. These ribbon alloys and films have some disadvantages when used as catalysts. The first is the lower surface area, and the second is oxidized surface layer. So special pretreatments are necessary to activate the catalyst. The pretreatment include the ancient alloy displacement, oxidation reduction, and polarization. It has been reported some amorphous alloys can be produced by reaction of gas ions with potassium chloride and sodium hydroxide in aqueous solution. The amorphous alloy produced by this chemical reaction is in the form of petrifying particles. In fact, Okamoto have studied the boron and nickel phosphorus samples for hydrogenation of some organic compounds. Recently, we have reported the nickel boron and nickel phosphorus samples prepared by this method are actually amplified amorphous anode particles, and because of the combination of amorphous structure and amplifying particles, these samples shows higher activity than their liquid anodes. Here I report some results on the hydrogenation of carbon monoxide on this catalyst. We prepared the nickel boron catalyst by the reaction of the chlorides and potassium chloride in aqueous solution. We washed the samples in ionized water for the removal of potassium and chlorine ions. Then wash the sample with absolute alcohol for removal of water. The samples were soaked in the alcohol for protection of the catalyst from surface oxidation by air. Then the samples was transferred to the base-bed bioreactor where the alcohol was dissolved in helium. Then the synthesis gas was introduced to the reactor. The hydrogenation of carbon monoxide was carried out on this reaction condition. We characterized the catalyst by using XRD and XPS. This is transition electron microgram of fresh catalyst. We can see from this figure the particle size is ranged from 15 to 50 nanometers. This indicates the fresh catalyst is ultra-fine particles. This is X-ray diffraction patterns. You can see only broad band instead of discrete peak in this diffraction patterns. This indicates the structure of the catalyst is in amorphous state. From the XPS results, we can see the elemental nickel and the boron atoms bound to nickel exist in the surface layer of the particles. Besides, another boron species also found to exist in the particle size, in the particle surface. This oxidizing species is originated from the hydrolysis of borohydrides, which absorb strongly on the surface of the particles. This is the catalytic activity and reaction product distribution. From this figure, we can see CO conversion on the fresh catalyst was 50%, and the main hydrocarbon were ethane, propane, butane, and butene. Increasing the reaction time, the CO conversion was decreased in the first half, then increased, and finally reached the steady state. It is interesting that the selectivity to methane was increased with the reaction time, while the selectivity to higher hydrocarbons was decreased after the reaction, after reaching the steady state. After reaching the steady state, the product was only methane. After reaching the steady state, the catalyst has lower surface area than the fresh way. However, the specific activity is calculated by taking account to the actual surface of the catalyst. A substantial increase can clearly be seen. In particular, the remarkable difference in the catalytic selectivity in different reaction steps cannot be explained by the particle growth. So we should take into consideration to the changes in the structure of the catalyst. Our XPS and XRD results evidence the changes in the structure and surface state of the catalyst. This is boron YS spectrum. This is the composition of catalyst verified from XRD. This is the spectral intensity of nickel to boron. It has been reported in the literature that dissociation of carbon monoxide may result in the oxidation of boron. In our cases, we also found part of boron will oxidize after reaction to now. Due to the oxidation of boron, this content in the amorphous phase may decrease. This makes the amorphous structure more unstable. After reaching the steady state, the boron alloy with nickel will oxidize completely, and the catalyst was completely crystallized and segregated from nickel, dispersed in the boron oxides. The XPS results indicate with the crystallization and segregation, the nickel species is enriched in the surface of the catalyst. So well known, the metal catalyst is a methylation catalyst. So the larger number of nickel metals and the great interaction between nickel and boron can account for the substantial increase in methylation activity. In summary, hydrogenation of carbon monoxide on electrifying amorphous boron alloy particles produce mainly carbon-4 hydrocarbons other than methane. The reaction results in the crystallization and segregation. After segregation and crystallization, the catalyst is a methylation catalyst for CO hydrogenation. Therefore, to maintain the high selectivity to carbon-4 hydrocarbons, it is important to maintain the amorphous structure stable. This work is done successfully in our laboratory with incorporation of phosphorus to the boron alloy. I will report these results next time if possible. Thank you for your attention.
I'm wondering, I would be a little bit concerned about heat and mass transfer effects in your catalyst when you're running 100% conversion. And I think that would have a significant effect upon both the chemistry of the catalyst and the product selectivity. Because I know with nickel and titanium, if you run at low conversion, 10 or 20%, you will make a substantial amount of C2 plus hydrocarbons. But I can guarantee you, if you run it at 100% conversion, you will see essentially only methane. And that has nothing to do with the structure of the catalyst. It's the fact that you have significant changes in the composition and you have heat and mass transfer complications. A quick question to check at it. If you increase the space velocity on your used catalyst, does the selectivity of the methane go back down?
table.
Yes. After 8 hours,
Yeah.
if you reduce the CO conversion
Yeah.
to a lower level, 40 or 50%,
Yeah.
does the methane selectivity go down?
Let's say that go. Let's say selectivity increase.
No. After 8 hours of reaction time, you increase your space velocity so you no longer have 100% conversion.
Yeah.
Have you done that experiment?
No.
Okay, thank you.
Thank you.
For the amorphous crystal form the ribbon form where it's manufactured by rapid quenching. A lot of its special catalytic properties are due to the particular structure of the ribbon, the catalyst in the ribbon form. How does your catalyst compare in structural form with the ribbon form?
Now the morning oral session is over. There's an announcement from the General Secretary. There are 2 buses waiting in the front of the building to take us to the restaurant. And the 2 buses will leave the restaurant at 1:20 to send us back to here. 1:20. The 2 buses will waiting for us at the front of the restaurant at 1:20.
Good afternoon, ladies and gentlemen. Please let us start the afternoon session number 3. We will share the chairmanship, and I am Ambo from University of Osaka. I will serve the chairman while pass the paper.
My name is Wu Yue. I am from the Changchun Institute of Applied Chemistry, the Chinese Academy of Science. Changchun, capital of Jilin Province, northeast part of China.
Okay, this is the first paper. The first paper is titled The Effect of the Air Pressure on the Properties of Aerogel of California and California shaker. The paper is presented by B.A. Robert, S.E. Ruggie, and E.I.O. Paper is presented by Dr. O. Please.
Thank you, Mr. Chairman. It is my pleasure to participate in the Trilateral Symposium this year. And what I want to do is afternoon to talk about some of the work we have been doing the last few years in using aerogels as catalytic materials. In my group, we have use the salt gel method to first prepare an alcohol gel and then extract it with supercritical CO2 to develop an aerogel. Our work is based mostly with metal alkoxide as a precursor. And in salt gel chemistry, the two steps are hydrolysis, shown here, giving rise to a partially hydrolyzed species, which then subsequently cross-link in the condensation step, shown here, giving us a gel. Now, the literature is full of examples showing the variation of salt gel parameters shown below in relation to the properties of the sample prepared by the salt gel method. My message to you this afternoon is that another less obvious parameter, namely the time it takes for a solution to turn into gel, has as much an effect on affecting both the physical and structural properties of the material that we synthesize. Now, in a sense, gel time is not a tunable parameter, such as the other parameters that I'm showing you here. On the other hand, as we shall see, that the effect of these parameters on gel time is critical in determining the material properties. Now, let me just briefly describe to you the reason behind making aerogels instead of the conventional zero gels. Once you obtain an alcohol gel in the salt gel synthesis, if you then conventionally dry the material, what happens is the liquid-vapor interface that exists inside the pores will collapse the pore due to the surface tension associated with that interface. We can bypass that problem using supercritical drying, in which the liquid-vapor interface can be eliminated since supercritical CO2 is used to extract the solvent, and then the CO2 is just vented without creating a liquid-vapor interface. One advantage of this is the integrity of the network is protected in the drying step, and because of it, we can form a high surface area aerogel. Let's then turn to the specific example that we're going to talk about this afternoon, namely first, the synthesis of a single component pure zirconia aerogel. What I'm showing you here is a recipe in which we use as a precursor zirconium amphioxide and as a solvent and propanol. The conditions of the synthesis in terms of the concentrations are shown here. So the actual procedure entails mixing two solutions containing water and nitric acid, and upon mixing and stirring, the solution is allowed to gel. Gel time in this work is defined as the time it takes for the vortex caused by stirring to disappear. Physically, that corresponds to the salt to gel transition, or an abrupt change in viscosity as the gel forms. After the formation of the gel, we then dry it with supercritical CO2. The material coming out of the extractor was then first vacuum dried under these conditions, and then held on at various temperatures for 2 hours to convert it into the oxide. Let me show you then the effect of water and nitric content on gel time. What is shown on this graph is gel time as a function of acid content, in this case nitric acid, at 2 water content levels shown by the ratio of 2 and 4. Now I wanted to first focus on the bottom curve where the water to zirconium ratio is a factor of 4. With very little acid present, we could not even form a gel. Instead, we got to precipitate. With increasing nitric acid content, the gel time starts to go up, i.e. a gel is formed, and the gel time goes up by several orders of magnitude. Even the actual amount of acid will only varies by less than 1 milliliter. The same trend was observed as we go to a lower water to zirconium ratio. With less water, then at each acid ratio, the gel time goes up because the concentration of the partially hydrolyzed species goes down, thus reducing the condensation rate. So we have seen that by changing either the water or acid ratio, we are changing the gel count. What effect does it have on the physical properties of the material? First, let's take a look at the property of surface area of zirconia aerogels after they have been calcined at 773 Kelvin for 2 hours. What we are showing here is the DEG surface area as a function of nitric acid content for the 2 series of catalysts synthesized for a water to zirconia ratio of 2 and 4. As you can tell, at each water ratio, that the surface area goes to a maximum at a specific acid content. If you have too little acid than the optimum, then in most cases you form a precipitate, and if you have too much acid past the optimum, again there's a decline in the corresponding surface area after the aerogel has been calcined to the same condition. Now, what I'm plotting here is gel time as a function, the surface area as a function of nitric acid. And I showed you already that nitric acid is also affecting the gel time. So of course one can then plot the surface area as a function of gel time directly. In other words, using gel time as the variable. And when you do that, you will again see this maximum. And here, in addition to the surface area, I'm also showing you the pore volume variation as a function of gel time. Now, from this point on, all the samples I'm going to show you are synthesized using a water to zirconium ratio of 2. And as you can see, as we vary the gel time, the surface area goes to a maximum. So does the corresponding pore volume, and the variation is indeed significant. Not surprisingly, the corresponding pore site distribution also shows this effect. And what we are looking here now is the pore site distribution for the various gel times that I showed you earlier. The bottom curve, a gel time of 0 seconds corresponds to actually a precipitated sample. In other words, the gel did not even form. As you go to very long gel time, in this case about 270 seconds, again you have a very broad distribution. Only by controlling the acid and water ratio to obtain a gel time of around 8 to 20 seconds, which I will refer to as an intermediate gel time, did we manage to synthesize the zirconia aerogel that has a narrow pore distribution containing mostly mesopores, and this particular zirconia aerogel has a surface area of about 120 to 130 meters per gram after calcination at 500 degrees Celsius. So what I have shown you so far is the effect of gel time on 2 properties, namely the BET surface area and the corresponding pore volume. What I want to do now is to shift gear a little bit and show you that gel time also affects the structural transformation of zirconia upon heat treatment. To set the stage for that, I would like to remind you of the phase diagram of zirconia taken from the literature shown here. Now, if you look at ambient pressure thermodynamic data, zirconia exists in the monoclinic form. Upon heat treatment to about 40 degrees Kelvin, then it will convert from the monoclinic form to the tetragonal form, and then finally from the tetragonal form to the cubic form before zirconia melts. When we look at the structure of our zirconia aerogels as a function of heat treatment, this is what we found. Let's first focus our attention on the upper panel, which represent X-ray diffraction patterns of the zirconia aerogels synthesized at an optimum ratio in order to maximize the surface area. And then we look at the X-ray diffraction result as a function of heat treatment. Notice that even after heat treatment at 673 degrees K, the sample remained X-ray amorphous. At 773 K, the sample did crystallize, but it crystallized into the tetragonal form. I would like to remind you that the bulk diagram suggests that bulk zirconia is stable in the monoclinic form at that temperature. Upon successive heating, the material did crystallize into the monoclinic form as indicated by the letter M in the X-ray diffraction pattern. Now, in order to confirm the structural assignments, we looked at the same series of samples using Raman spectroscopy shown at the bottom panel, and the structural assignments agree. Again, at low temperature, the material is X-ray amorphous. It first crystallizes into the tetragonal form of zirconia, and then upon further heat treatment into the monoclinic form. Now, the fact that we can stabilize the tetragonal zirconia first before the transformation to monoclinic in itself is not a new finding. In fact, many other investigators have reported the stabilization of tetragonal zirconia at room temperature. On the other hand, the literature is still divided as to what is the cause of that stabilization. One possibility is the crystallized size effect as proposed by Garvey and others. In that when you have very small particle, then the surface free energy term dominates, leading to the tetragonal form being the more stable form. We would like to present some new results suggesting that crystallized size effect by itself is inadequate in explaining this structural stabilization. There's a lot of information on this graph, so let me lead you through it. First, I want you to focus on the bottom slide. With gel time now as a variable that we can systematically vary, we look at the crystallized size determined by X-ray diffraction non-broadening as a function of gel time. Okay? At zero gel time, basically we're looking at a precipitated sample, and then we have over this plate 4 different gel samples prepared as aerogel in which we vary the gel time. We took all these samples to 773, 973, and 1173K. We determined the structure by X-ray diffraction, measured the crystalline size by non-broadening, and then found the following. First of all, for the precipitated sample, we could actually stabilize in the T form, and this material actually has a larger crystallized size than some of the M form we stabilized by heating the aerogel up. At the same time, when we look at the bottom, the top diagram, in which we actually monitor the fraction of tetragonal zirconia transformed into the monoclinic form, we observe the following. At 773K, all the materials are stabilized in the tetragonal form, irrespective of the gel time the material is prepared. Also, by the time we reach 1173K, all material transformed in the monoclinic form. In the intermediate heat treatment of 973K, then we observe a very interesting trend. Namely, the fraction of conversion from tetragonal form to monoclinic form is a function of gel time. Now, let's try to put these two diagrams together. For the precipitated sample, which actually have an average crystallized size larger than all of the aerogels, that material actually transforms into the monoclinic form easier than the other materials. And at the same time, when we compare the series of samples over gel time, we actually see again variation of the transformation as we heat the sample up. Now, our interpretation of this result is schematically shown here. What we are proposing is crystallized size in itself is an insufficient parameter in dictating the transformation. But rather, it's a combination of the crystallized size of the particle as well as, quote-unquote, the quality of the particle. By that I mean, in order to facilitate the tetragonal to monoclinic transformation, we have to have nucleation site within each particle, which is broadly defect-oriented. Think about the problem the following way then. By controlling the gel time, we now have a unique way to actually bring materials out of the solution of different quality in terms of the size of the particle as well as the number of defect density within those particles. So what we think happens is the following. Then when we have short gel time samples, by that I mean anywhere from 0 to 5 seconds, that we just have precipitate come out of solution that have large particles, and the fact that they come out of solution so rapidly means that they have a lot of defect density, thus facilitate the transformation upon heating. And this is the one sample that even at 973K, they totally convert into monoclinic form. By allowing the gel time to close up, we basically, in essence, allow the polymeric level to grow, and in the process, we stabilize smaller particles. These particles still have defect size into them, but now the transformation is retarded, and we see that variation as a function of gel time. And finally, by allowing the gel time to go even longer, to a minute or more, what we do is also grow much larger particles, and at the same time, by allowing the particles to grow more slowly, in a sense, it's a low temperature way to anneal out the defects, and we found that these particles actually resist the tetragonal to monoclinic transformation better, even though strictly on the size alone, there's no difference, or not a large difference in size between these two particles. So I think what I have shown is that by controlling gel time, we actually have an interesting way to control not only particle size of the material coming out of the solution, but also the quality of the particles in terms of defect densities. Okay, at this point, in the remaining few minutes I would like to switch gear and again carry this concept a bit further to show you that gel time is an equally important parameter when we try to do two-component synthesis. The specific example that I want to talk about is simply to add silica to zirconia in synthesizing a zirconia-silica aerogel. Now, in this case, the zirconia and silica precursors have very different reactivity. In fact, the zirconia alkoxide reacts a lot faster than the silicon alkoxide. So in order to balance the difference in reactivity, we adopt a procedure that's commonly practiced in the soil gel literature, namely prehydrolysis. Very simply, prehydrolysis is to allow the less reactive alkoxide to react with water first so that it can catch up upon the addition of the more reactive alkoxide. We approach this synthesis by doing two series of samples, the non-prehydrolyzed step, in which we basically mix everything together, versus the prehydrolyzed step, in which the silica precursor is allowed to react with water for 10 minutes prior to the addition of the zirconia alkoxide. Now, having identified gel time as an important parameter in the zirconia world, we actually have to come up with a scheme by which that we can actually isolate the effect of prehydrolysis from the effect of gel time. And this is accomplished by the following scheme. We have the following experimental design. We for a specific combination of zirconia and silica, we first determine the gel time for a prehydrolyzed sample. Okay? We then remove the prehydrolysis while keeping all the other conditions the same. Allow the gel time to go to whatever value it is. In this case, it's T prime, which is longer than the gel time with prehydrolysis. We add the prehydrolysis back on, and then use acid as a tuning variable to bring the gel time back to the same value. The best way to appreciate this is actually the bottom graph, in which we are looking at the gel time as an acid ratio, and this is what we refer to as a stair-step synthesis. In other words, at a specific acid ratio, we vary the gel time by taking out the prehydrolysis step, and then at each constant gel time, we vary the acid ratio in order to compare hydrolysis versus non-hydrolysis sample. Now,